All right, this is 18.3, resistors in parallel and Kirchhoff's laws. Today we're going to calculate resistors in parallel, which will be just as easy as resistors in series, so that part won't be very long. And then we're going to learn Kirchhoff's laws to solve a circuit. This is talking about combined circuits and usually with multiple batteries. So the rules are kind of weird, and we'll take a little bit of figuring out, but we're not going to go too deep into it. We'll just show you how to solve it and learn some problems on it. And tomorrow we'll have a worksheet on it. So first of all, resistors in parallel. Last time we learned about resistors in series that are connected by one wire. So parallel circuits have T sections in between them. Let's draw you a little picture. So here's a resistor. And here's another resistor. These two would be in series. Now, if we went this way, and it broke off to a resistor here and a resistor here.
You could make a really complex circuit with that. Because
Yes.
then, if each of those broke off into other circuits,
Let me add a battery in here so it's
So
There you go.
what two resistors in parallel?
So these resistors are in series.
I want
These two resistors are actually in series. You see them? They're in
Oh, but the
series.
two
Because
series
they're
are
in that
parallel,
loop
sort of.
right there, sort of. Kind of did it weird.
you could put them on the bottom.
Yeah, I was going to say, let me put one here instead. So that it's a little bit more clear.
You got obliterated.
There we go. It doesn't have to be perfect.
Whoa,
Just kind of
that's
something like that.
okay.
We just draw in the fingers of this.
There we go. Done. Okay, so these two are in series. But these two are in parallel with these two. So let's look at a simple circuit. Parallel. So what I'm trying to point out is that even though there's some T sections between these, like if you went this direction, you could see a T section here. As long as there's one between those resistor, it becomes a series. So series is a priority. If you have one wire between two resistors, it's automatically a series. But these ones, there is no one wire between them. We have two T sections, so we're stuck. It's got to be parallel. So these ones are parallel. So when circuits are in parallel, we have a couple of different rules. Our rules for parallel is that when you add up your resistance, let's start with constant. Your voltage is constant. Your current is added. And your resistance is added up inversely. And you're like, okay, what is that? It means that for each resistor, you're going to do 1 over that resistor, add it to the next 1 over that next resistor, and it should equal 1 over the total resistance. So a lot of times you'll end up with some sort of number here, and a lot of people get stuck. Just flip-flop the bottom and the top. Questions? No questions? Should be pretty easy. So here is the rules, and here is the equivalent resistance. So these are each in parallel with each other. There's T section, some sort of section where all the wires connect between each one of these. There's no single wires between them.
Excuse me. Thank you.
Just to get this straight line. That's a battery.
Yes, this one, the 18 volts is a battery.
And then that's the resistor.
Yes. And the resistor could be like what we actually call a resistor. It could be like a light bulb. or a heating element or something. All right, resistors in parallel. We're going to combine together the resistances first to find the total resistance. So that's adding up your resistors inversely. Then you will find the total current, usually because you'll be given voltage, using V equals IR. Once you know V, actually you know V, so V is constant. It'll be through the whole thing. You can solve V equals IR for each current to solve for the missing I, and then P equals IV to solve for the missing P. Add up your P's and make sure they equal the total P to double check. So we're going to do that here with this practice. It says 3 resistors are in parallel. They receive the same amount of voltage of 24 volts from a single source. What is the resistance of the system, current of the system, potential difference across each resistor, power in each resistor, and power total. So you can use the grid to organize your information. If you would like to answer them all, one at a time, that's fine for these simple circuits. But when we get complex stuff, that's probably not the way we want to go. So here is our nice simple circuit. We have 1, 2, and 3 ohms and a 24-volt battery. This is VERP. All right, we're going to add up our resistances. 1 over 1 plus 1 over 2 plus 1 over 3 gives us 1 over the total resistance. .83. So the total resistance is going to be 1 over 1.83. And that gives us a total resistance of 0.546. Is that what you got?
Yeah. Well, roughly.
Roughly, yeah. All right. Our voltage is constant, so 24 all the way across. And then we can just solve for current on each of these using V equals IR. So 24 equals 1 times.
Sorry. You okay? Me too.
Are you dead?
So this will be 24. 24 divided by 2. 24 divided by 3. 24 divided by
That number.
0.546. 44 roughly. You can double check right here. You can go 24 plus 12 plus 8. Does that equal 44? Yeah, it does. And then we can do P equals IV. So 24 times 24. No. P. Sorry, I'm doing each one right now. This is just my sample. 6, 24 times 12. 288, 24 times 8, 192, 24 times 44, 1056. Now let's add these up and make sure they equal what they're supposed to. And it does check out, so it's good. Now this is great for parallel resistors. No problem. It's nice and easy. When they get to complicated circuits, which we'll do on Monday, you're going to see it's a little bit trickier. Same rules, just you have to use them in different pieces. Okay, the rest of today is talking about Kirchhoff's laws, and you have to bear with me because I'm not very good at them. So Kirchhoff's laws are used to find the current flow in the circuit, or they use the current flow to figure out stuff in the circuit, like missing resistances, voltages and currents. One of the things that you need to remember is that the flow of electrons is actually opposite to the direction of the current. That's, just have it in the back of your mind. I don't think it's going to hinder you too much if you forget.
Okay, so what we're doing in this chapter is pretty much what we've been doing in the last chapter, except it's 1 over R.
Are we talking about section?
Yeah.
Okay, yes, with parallel circuits. But right now, this slide, we're moving to the next section.
Okay.
This is actually found in 18.4. Okay, now what we're going to do is I'm going to teach you more rules. There's 2 rules, the junction rule and the loop rule. The junction rule says that anytime you have a junction, a T spot where the current splits, you can add up those junctions at that point to equal the total current. And that's because, current is in parallel and it's added in parallel and it's constant in series. So when you add them up, the current here and the current here, it should equal the current of it coming into the circuit. So the junction rule says that if this is I1, this is I2, and this is I3, then I1 should equal I2 plus I3. That's the junction rule. That's the easy one. Now the loop rule is a little different. And it says the sum of the voltage across all the elements in one closed loop must add up to equal 0. Now remember, voltage can either be a battery, voltage, or it can be a resistor times I. So V equals IR. So anytime you come across a resistor, use IR, and anytime you come across a battery, you use E. And again, we usually use Kirchhoff's rules for things that have circuits with multiple batteries in it, because they're not, this stuff. Okay, got the basics. Here's a picture of the junction rule. I kind of wrote this on the board for you. Okay, you got it? Junction rule. This is a conservation of charge. So it says if the charge going in has to equal the charge coming out. And then the loop rule says that all the voltages in one loop have to add up to equal 0. And this has to do with your potential difference, right? Your battery. If you think about when you're going around parallel, when you go around in series, all your voltages have to add up. So what they're saying is if 40 volts is going into this, then these two things need to be using that 40 volts. Something like that. Not quite that way. Pretty much. So it has to add up to equal 0. You can use any loop you want. It doesn't just have to be this loop. It could be this loop. It could be this loop. It can be this loop. It could be the entire outside loop. It could be this loop. So it doesn't matter what loop you pick. What's tricky is, do you give it a positive or a negative? And I struggle with this too. That's probably the worst part of it. Is it positive or is it negative when I go around? The best way to do it is to assign a current direction to each thing. So when we go around in this picture that's up here, it said that the current is going down in each one of these. So it comes out of the battery, it's going down, it's going down, it's going down. I don't know if that's quite correct because you can see that the short end is on this side, and this one it should actually be going up this direction. And this one should be going up that direction. So you should have currents going up and then around.
Oh, so weird.
Yeah. So, it's a little tricky whether you make it negative or positive, and a lot of times it shouldn't matter too much. I found that when I'm doing the problems, if I do assign a wrong direction, I end up getting a weird number sometimes just because of the math. But what they say is if you assign the wrong direction, it just makes the answer negative, which sometimes that happens to me too, and I end up having the right numbers, just the wrong direction. So it's not a big deal. You're just like, oh, it's just going the opposite direction, which I said. But sometimes it does mess up the numbers. I can't tell you what the best way is to do it other than just practice them. And again, I'm still not an expert at these either.
You got 4 words, 4 two-letter words starting with I in that sentence. That's weird.
I actually copied this from Google's PowerPoint, this particular slide. Okay. So when you're getting the equations for the loop rule, when you transverse the current, and as we're moving left to right here, so if you're moving you're moving around in this direction of your loop. So like I said, I'm going around this way in the loop. Remember to assign your currents first. Just give it a direction, going left, going right. So if you're going from here to here, if you're going across the resistor in the same direction in which the current is going, it's negative. If you're going in the way of the resistor in the opposite direction, so if you're moving this way and your loop is going this way and your current is in the opposite direction, then it makes it positive. And if you're going from the little bar to the big bar as you transverse it, your E will be positive. So if you go from positive to negative side, the positive terminal to the negative side, then it makes it a negative.
Wait, the resistors, how do you tell which side's positive?
You don't. It's the way which you're assigning your currents in the beginning. So for instance, here is a little circuit here. With this, I would look at it and be like, okay, if I am a current, most currents start out going from negative to positive, so that's going to be my I. And then it can either, well, for this one, I'd probably do I going this way and I going this way. So when it splits here, it's going to go. So if I'm looking at a loop, and again, it doesn't matter which way you transverse the loop. You can pick any loop you want. There's 3 loops here. We have 1, 2, and then the outside 3. So it doesn't matter which one you want. You just need as many equations as you have missing variables. So we can use a junction rule right here. If this is I1, I2, and I3, our junction rule would be I1 equals I2 plus I3. A loop rule, again, it doesn't matter which way you transverse it, so let's go this way. This would have some sort of voltage. It will be some, like, let's call it E. So for our first equation here, 0 is going to equal E, because I'm moving in the loop, I'm moving this way, from negative to positive, so we have a positive E. Then, when I go here, that doesn't count for anything. And right here, this is still I1, by the way. I2 is anything on this line, I1 is anything on this line. So this would be I1, let's call this R1. Since the current is moving this way, and I'm moving in the same direction across this resistor, this way, with my loop, they're in the same direction, so we're going to have negative I1. So this will be minus I1 R1. So there's one loop. Let's do another loop. Let's do this loop, the outer loop, this way. So since I'm moving this way across E, it's still a positive E. I have this one, it's in the same direction, so that's going to be a negative I3, and let's call this resistor 3, resistor 2, I2. Okay. And then this one, still in the same direction, so negative I1 R1. I should have put another resistor there. Yeah, I say there's not going to be another loop because that's all we have. Because this one doesn't really count for anything. So I didn't put a resistor there. That's what happens when you're working on circuits, things get a little long. Okay, so there would be 3 different equations that you can get from this one using the loop rule, and this one just takes practice, honestly. It's just do them. So I actually do have one for you, a little practice for us. Nope, doesn't want to do it. Doesn't like it.
Are those 2 power sources?
It is 2 power sources. Okay, I'm going to redraw. 12 volts.
I'm assuming current will not go backwards through the battery.
You can assign it that way, but when you get the
And
current,
then like
it'll be
the 12 volt will not push power back through the 8 volt.
yes.
Wait, yes, wait.
It will.
Okay, so
Should.
the battery on the
Oh, so they come together like
Yeah.
water.
BTW on the homework, one of the problems, apparently the arrow, they put an arrow and it's wrong.
Let me double check.
Yeah,
that.
there is one where it is wrong. I know, I remember that problem.
Yeah, that's when it's like, yeah, some sneaky person put the arrow backwards to confuse you. I'm like, I like that description.
Yeah. Is that right?
So that means that the battery on the left can't send power towards the battery on the right. It has to go through that middle.
Yes. All right. This is R1, which is 4.
Like when 2 waves hit each other, they
R2,
grab
this
in
is
the air.
3. And R3, this is 2. Well, that's confusing. All right, and then we have E2, which is 8. And this is, I guess this is E1. Okay, so the first thing you want to do is designate your current. Now, you start with the battery. So this is a little one and that's a big one. So the current is going to be I1, and that'll take care of anything on this line. And this one is going to go that way, so we'll call that I2. They're going to come together right here, and they're going to be forced down this way. This will be I3. So I1, I2. That will leave us with our first rule, the junction rule, which is the easiest one, is I3 should be made up of I1 and I2. Okay, so now we're going to transverse the loops. Again, it doesn't really matter if you go clockwise or counterclockwise. I usually try to make E's positive when I'm choosing loops, but it doesn't really matter. It'll all wash out in the end. So let's go this way around this loop, the little one right here. We have and it's in the same direction across the battery that it's supposed to be, so it should be a positive E1. This is in the same direction, so that'll be a negative 4I1 for the resistance. I didn't put in R, I just put in a number. And then we're going to go across this resistor in the middle, and that'll be a negative as well because it's in the same direction, and that will be a negative 3I3. So that's the first one. Let's pick the next way to be this one around this circle. Again, I try to make my E's positive, which is why I picked that way, but it doesn't matter. You can go either way. This will be E2 is positive because it's in the same direction. Across this resistor, negative because it's in the opposite, or it's in the same direction for the resistor. And then this one is also in the same direction. The I is also going this way because it comes down this way. So this one's going to be negative 2, and it's going to be I2. So there's another one. Now, we're looking for the current in each one. I1, I2, and I3, we have 3 equations. We don't need another loop. But if you really want to make another loop, there is another loop in here that we can get. So let's just look at it. We might not use it because why would we do more work than we have to? But let's do the outside here. I'm going to look at the whole thing on the outside. So we'll start with this one. Since we're going backwards, now we have a negative E1. And this one's in the same direction, so a negative 2I2 for the resistor. This one's in the correct direction for the E, so positive E2. And this one's in the opposite direction, so positive 4I1. So we've got battery in the opposite direction, resistor in the same direction, battery in the same direction, and resistor in the opposite direction. I think I said that right. So we have 4 equations even though we only have 3 unknowns. The other thing that I'm noticing is that I put in the resistances, but I didn't put in the E's. It's kind of silly. So I'm going to just go and replace those E's with actual voltages. E1 is 12. E2 was 8. There you go. That will let you kind of skip this a little bit. Okay, the best way to do this is to find the common. You have I3 in each one of these. So I would solve this equation for I1 and this one for I2, and then plug it into the top equation. So I'm just going to look at this one real quick. And this one is 4I1 plus 3I. Wait, I wanted to solve for I1, right? So I need to get I1 by itself. Wait, so we have 4I1 equals 12 minus 3I3. I1 equals 3 minus 3/4 I3. So there's one equation. Let's look at this equation now. We want to get I2 by itself. So 2I2 equals 8 minus 3I3. I2 equals 4 minus 3 over 2. I3. Now we're going to plug into this equation up here. So I3 is going to equal 3 minus 3/4 I3 plus 4 minus 3 over 2 I3. I3 equals 2.15. And now all of these should be in amps. So make sure you put in your units. How do you guys feel about this?
I'm confused. I don't think 3.25 is right.
No?
No. 1.5 plus 0.75 is 2.25.
You're dividing.
Oh, I see what I did. Okay.
Nick, does it look right?
Yeah.
You bet it looks right. You made a mistake. You guys are usually the ones that can pick them out. Okay, I've got some clicker questions for you today. I don't think there's too many Kirchhoff stuff in there. I think most of it's parallel stuff. And I do want you to try your best on the Kirchhoff rules and know that it's hard. There won't be a lot of it on the AP test, but they did say they were going to cover it. So I want you at least exposed to it.
Wait, just like question here about that. When they're like sending you the documents to tell you stuff like that, like what we're going to be tested on in the AP exam, can you show that to us directly?
You can look it up on the website. Yeah, just go to AP Physics 1. It'll show you everything that I'm supposed to teach you.
Cool.